Hello and welcome to another EE140 video. In preparation for our upcoming midterm 2, we are going to do a problem about normal incidence and wave polarization. So let's go ahead and take a look at our example over here. So notice that we don't have any diagram or illustrations, so we need to dissect this problem carefully. Alright, so we're given a 159 megahertz frequency. So from that we could extract our omega, and that's just going to be 2 pi f. That's 2 pi times 159 times 10 to the 6, and we simply get 9.99 times 10 to the 8, or we could just simply write down for omega 10 to the 9th. Okay, so next we are given LHCP, or electromagnetic wave, that is incident normally along the y direction. Okay, so we could draw our z direction. So if this is our z direction, we have an incident wave that is normal to it, like this. Alright, and that is coming from air onto a lossless dielectric medium. Epsilon r equals 4, so that's boundary condition. So that's coming from air, which ER or epsilon naught of 1, then going into epsilon naught of 4 medium, and that E naught of I at origin is 2 volts per meter along the x direction. Okay, so if we could designate this our x direction. Now the problem is asking us to get the incident E sub I and reflected E sub r wave expression. Okay, so to get those, first we need to take care of this one, LHCP, and let me just redraw the axes. Okay, let's let this be y, let this be x. Now with our right hand rule, this one is our thumb, y-axis is our pointing finger, and z is our middle finger. Remember, this is for the axes, and for that we always use our right hand. So with that, middle finger, thumb, pointing finger, we can determine that z, or positive z, is going into the page, while negative z is coming out of the page. Right? Now you might ask, why did I need the z-axis on an xy plane? That is to illustrate LHCP, but we'll come back to that in a second. Now we do have a wave that's traveling from air into something else. Right? That tells me that our k, or wave propagation direction, is going along the z-axis, and with that we can determine that k's of I, or incident, is equals to k naught z hat. Now if we're going to calculate for the value of k, we can do so. We can do that by this relationship, W over K is equals to C. Therefore K is just simply W over C, and that's just going to be 10 to the 9th divided by speed of light, 10 to the 3, or 3 times 10 to the 8, which just comes out to be 10 to the 9, 3.3 0.33. So that's going to be our K. It's just now that we have our K and we know that it's traveling along the Z, positive Z axis, we could write it down here that K sub I is also going into the page. And now that we know the direction of K, we could illustrate this LHCP, and over here we know this is E0 of I, the magnitude of 2 volts per meter, E0 of I. So if with our thumb sticking into the page, our fingers lined up along the x-axis, if we curl our finger, notice that it's going this way towards the negative y direction. So that is our, if this is where we came from, that's our t equals 0, and this one is our t is greater than 0. So pretty much it's moving this way. Alright, and that's according to left hand circular polarization. So that's pretty much what this statement over here is trying to tell us. Alright, so for incident, it's going this way, at least for incident. Alright, so now we could start writing down the components for our E sub I wave expression. We could get started by writing down E1 of t, or I'm sorry, E1 of I. Alright, and usually, or the format is going to be direction, magnitude, phase, and finally unit. Okay, so E1 sub I, we know that initially it's right along the x-axis. Alright, so that's just going to be x hat. Now we know that magnitude is given to us by this, so that's just going to be 2. Now what about the phase? So we know at t equals 0, the whole function is not 0, so that means that it has to be a cosine over here. We'll put in our omega t plus, or wait, now we have to determine our k. We have the value for k, but is it going to be minus here or plus? Since the value here is positive, then over here it has to be negative. 0.33 z, that's along positive z direction. Alright, so that's our E1 sub E. Now we can move on to E1 sub I. Now we could move on to E2 sub I. Keep forgetting these arrows, so forgive me for that. Now, what's going to be the direction? We know that it's moving. Here, maybe this one will be better. So we know it's moving from the positive x direction towards negative y. It's indicated here. I don't know if you guys can see that. So the direction for our second term has to be negative y hat. Magnitude is going to be the same at 2 volts per meter. Now remember this, cosine, so this one has to be sine because they're out of phase 90 degrees. And we just write down our omega again, minus 3.33 Z. Oh, don't forget our unit. Now we're ready to write down our E sub I, or E incident wave expression. Okay, so that's E of I. We just combine these two. So we have x hat 2 cosine omega t minus k, or I'm sorry, 3.33 along the positive z-axis minus y hat 2 sine omega t minus 3.33 z. That's going to be volts per meter. Alright, now that we have our E sub I equation, or wave function, wave expression, we can just put a box in there. There we go. So now we are left with so we took care of this one. We are just left with finding the wave expression for E sub R. So let's scroll down here. But how do we find E sub R? So let's stick to what we're given. Okay, we are given 2 E sub or epsilon R permittivity, and remember this N, which is index of fraction, is just equals to root of E's, or epsilon R. Now, quick reminder, this is just for non-magnetic materials only. Alright, so that tells us that these two are non-magnetic. That's okay. So we have N sub 1, and that's going to be coming from air, so just root of 1, and N sub 2 coming from here, it's just going to be root of 4. From there, we could write down our gamma, which is, let's use different color pen, let's use green, see how it comes out, and that is the fraction of reflection, and that is just equals to N1 minus N2 divided by N1 plus N2. And again, quick reminder, this is for non-magnetic materials only. Alright? And that includes this equation over here that we just wrote down. So with that, we could just substitute, excuse me, root 1 minus root 4 over root 1 plus root 4. And that just comes out to 1 minus 2 is negative 1 over 3. Alright, so this is our gamma, remember? By the way, gamma is also equals to E naught of R over E naught of I. And that is what we're pretty much going to use to find our wave expression. Okay, So with this coming from our gamma, we can now figure we have the value for E naught sub I, and that is given by 2 volts per meter. All right, and we have this relationship over here, negative 1/3. So now we could just solve for E naught of R. It's just going to be negative 1/3 times E naught of I, which is 2. That comes out as negative 2/3. Now that we have that, we could get started using or writing down our E sub R wave expression. E sub R for reflected. And again, it's going to be the same format. Okay. So for the direction, we know that it's going to be the same as our E sub I or E incident. And since E of I is right along the x direction, then E sub R direction is also x direction. Alright. Now our magnitude, since it's negative 2/3, right, we'll let that declare the true direction of E sub R, but we'll do that in the next step. So magnitude, we got that. Direction, we have that. Phase, so again it's going to be cosine, the same omega, 10 to the 9 times t. Now the question is it going to be plus or minus k? First off, let's find out what k sub r is. Right? So we know k sub r is just the opposite, or the other direction. It propagates the other direction than k sub I. And since we have k sub I traversing the positive z direction, then that means that k sub r is just equals to negative k naught z hat, or otherwise it's traversing the negative z direction. Right? So since it's negative k naught z hat, and we have a value of 3.33 for k, so it's gonna be negative, so double negative, that makes it a positive 3.33, because remember over here we have positive k, but we wrote down as negative 3.33. Now the same thing applies here, because it's negative k, so it's negative, and therefore it's going to be positive 3.33 z hat, or z, I'm sorry, just z. Now what's the other part, or the other term? It's still going to be y hat. Alright, but what's the sign? For now, let's write down positive, because we'll let this magnitude determine the direction, right? And again, it's going to be 90 degrees out of phase, so it's going to be sine times omega t plus 3.33 z, and that's in volts per meter. Now let's just finalize this. So we have a negative sign here, so you can agree with me if I write it down this way, right? Cosine 10 to the 9 t plus 3.33 z. Now we have negative here and positive here, so that's just going to be negative y hat, and then 2/3 sine omega 10 to the 9 t plus 3.33 Z, and that's volt per meter. Now we've done our E's of R or reflected. We have the wave function for it, okay, or wave expression. Now question is, are we done? Let's go ahead and take a look. Unfortunately, it's still asking us for what is the polarization state of the reflected wave, and we have to answer that whether we like it or not. So let's see, how do we figure that one out? All right, so let's take a look at this one. All right, it's negative x direction, so let's write it down. So if this is x, this is y, this is negative x, this is negative y. All right, and also just to be sure, let's copy, since we have x y plane, and from that we know that z, or positive z, is pointing into the page and negative z is pointing out the page. Let's copy that over here. Alright, so z is into the page, negative z is out of the page. Alright, so why did I do that? Because we need to illustrate where this case of R is going. So we know it's traversing the negative z hat, or negative z direction. So we could write it down over here. Let's see what blue should do. So case of R, I don't know if you guys can see that, is going out of the page also. Alright, what else? So we need, or we know that the first term of E's of R, or E reflected, is along negative x-axis. So let's just sketch it. Actually, let's green. So it's over here. Initially, right? So we know that that is our t is equals to 0. Alright, now let's look at the second term. I'm sorry, I just realized I made a mistake, so let's just go back here. So I wrote this down. I wrote this down initially as positive y when it should be negative y, because we just copied the direction, remember, from E's of incidence, which is positive x and negative y. So I copied it here. So this one should be positive y. I do apologize for that confusion. Okay, and this one should be negative. Still, same rules apply. We'll let this determine our direction. So that's negative times negative equals positive. Right? Do apologize about that, but I just realized it as we were trying to draw here. So now that we know that it's going from negative x direction, which is this, going to positive y direction, we know that it's going to be moving that way from negative x to positive y. Alright, so if this is our t equals 0, this is our t greater than 0. Alright, now how does that answer whether it's right hand or left hand circularly polarized? we'll do this. Alright, so let's write it down. RHCP or LHCP. Right? So let's take a pick. I'll pick left. Alright, and then I'm gonna try it out, see if it fits this transition going that way. Okay, so with my left hand, I would stick my finger out of the page because that's where case of R is going, and then I would line down my fingers along the negative X direction because that's where initially it starts. Now I'm gonna curl my fingers. Alright, and doing that, I found out that it's curling this way. Alright, and obviously that's not the trajectory we wanted or the movement transition we wanted. We want it going to the positive y, not the negative y, right? So that means this is not left hand circularly polarized, but right hand circular polarization. So from that, what can we conclude from? So we can say that E's of R, or reflected, is right hand circular polarized state. Okay, and that is what it's asking here. What is the polarization state of the reflective wave? So the reflective wave, E's of R, is RHCP state. There we have it. I hope this is clear. If there was any confusions, I apologize. But if you're still left with any questions, go ahead and approach our TA, or better still, ask the professor himself. Thank you for watching and have a great day.